Hello everyone, welcome to Smart Guru Learning. In today's video, we will take a look at the alpha-ketoglutarate dehydrogenase mechanism. Alpha-ketoglutarate dehydrogenase is an enzyme complex that catalyzes oxidative decarboxylation of alpha-ketoglutarate to succinyl-CoA. This mechanism takes place during the TCA cycle or the Krebs cycle. This mechanism is very similar to the pyruvate dehydrogenase complex mechanism that converts pyruvate to acetyl-CoA. Pyruvate is produced through glycolysis. Pyruvate dehydrogenase mechanism converts this pyruvate to acetyl-CoA, which is further used in the TCA cycle for further energy production in the form of ATP. I have provided the link for the pyruvate dehydrogenase complex mechanism video in the description below. So I recommend you to watch that video if you have not already, because this might be helpful to clearly understand the concept and the similarities between these two mechanisms. Like the pyruvate dehydrogenase complex mechanism, alpha-ketoglutarate dehydrogenase consists of three enzymes. Enzyme 1 is alpha-ketoglutarate dehydrogenase, which decarboxylates alpha-ketoglutarate. In the pyruvate dehydrogenase complex mechanism, enzyme 1 is pyruvate dehydrogenase, which decarboxylates pyruvate. Enzyme 2 is dihydrolipoyl transsuccinylase, which transfers the acyl group to coenzyme A. In the pyruvate dehydrogenase complex mechanism, enzyme 2 is dihydrolipoyl transacetylase, which transfers the acyl group to coenzyme A. Enzyme 3 is dihydrolipoyl transacetylase, which regenerates lipoic acid or lipoid from dihydrolipoic acid and reduces NAD+ to NADH. This enzyme is the same enzyme that is used in the pyruvate dehydrogenase complex mechanism. Like the pyruvate dehydrogenase mechanism, alpha-ketoglutarate dehydrogenase mechanism involves two cofactors, thiamine pyrophosphate and the lipoic acid or lipoid. Thiamine pyrophosphate or TPP is an active form of thiamine, commonly known as vitamin B1. This cofactor is important for carbohydrate metabolism and energy production in various mechanisms and pathways. Therefore, inadequate levels of vitamin B1 or thiamine may lead to various critical health issues, mainly related to the nervous system, due to insufficient production of energy, metabolic dysfunction, and oxidative stress. Here is the full structure of TPP. The portion highlighted in blue is the basic structure of TPP that is mainly involved in the mechanism. Therefore, when understanding the alpha-ketoglutarate dehydrogenase mechanism, I will only draw this basic structure instead of drawing the full structure so that we can understand the mechanism clearly. Another cofactor that is involved in the alpha-ketoglutarate dehydrogenase mechanism is lipoid or lipoic acid. Lipoic acid is an important enzyme cofactor which is vital for various mitochondrial enzyme complexes and therefore an important factor in energy production. Therefore, various mitochondrial dysfunctions may occur if a person has the inability to synthesize lipoid. It may lead to the lack of energy production and accumulation of toxic amino acids. Besides this, it is also an important cofactor of enzymes that are involved in catabolism or the breakdown of leucine, isoleucine, and valine, which are referred to as the branched chain amino acids. Here is the full structure of lipoic acid. The portion highlighted in blue is the basic structure that is mainly involved in the mechanism. Therefore, like TPP, I will only draw this basic structure to understand this mechanism clearly. Other cofactors that are used in this mechanism are coenzyme A and NAD+. Now, let us take a look at alpha-ketoglutarate dehydrogenase mechanism. Step 1. Decarboxylation of alpha-ketoglutarate by enzyme 1 alpha-ketoglutarate dehydrogenase. Alpha-ketoglutarate has a carbonyl group here, and this carbonyl carbon is electrophilic or electron deficient. This is because oxygen is more electronegative than the carbon, due to which the electrons are pulled more towards the oxygen, making the carbonyl carbon electrophilic with a partial positive charge. Therefore, TPP acts as a nucleophile and attacks this carbonyl carbon, and the electrons in this double bond are delocalized to the oxygen. Through this, we get an intermediate that looks like this. Next, the electrons from this oxygen move here and form a double bond. The electrons from this bond move here, and through this, carbon dioxide is released. Then, the double bond here in the TPP moves to this nitrogen, and with this, we get an intermediate with succinyl group attached to the TPP. Step 2. Transfer of succinyl group to lipoic acid or lipoid by enzyme 2-dihydrolipoyl transsuccinylase. The electrons on the nitrogen move back here to form a double bond, and the electrons in this double bond acts as a nucleophile and attacks lipoid here. The bond between the sulfur groups here is broken as it attacks hydrogen that is attached to some base. Through this, lipoic acid is reduced to dihydrolipoic acid. Through this, we get an intermediate that looks like this. The electrons from the oxygen move here, and the bond with the TPP is broken and the TPP is released. With this, we get an intermediate that looks like this. Step 3. Transfer of succinyl group to coenzyme A. Coenzyme A then attacks the carbonyl carbon here, and the electrons from this double bond are delocalized to the oxygen. Through this, we get an intermediate like this. The electrons from the oxygen move back here to form a double bond, and the bond with the dihydrolipoic acid is broken and released. In this way, we get an intermediate that looks like this with the succinyl group attached to coenzyme A. Step 4. Dihydrolipoic acid to lipoic acid by enzyme 3-dihydrolipoyl dehydrogenase. The negative charge on the sulfur group acts as a nucleophile and forms a bond with this sulfur. The hydrogen is transferred from this sulfur to the NAD+, and it is reduced to NADH, which is a high energy electron carrying molecule. With this, dihydrolipoic acid is oxidized to lipoic acid. Here is an overview of the alpha-ketoglutarate dehydrogenase mechanism. If we compare this mechanism with the pyruvate dehydrogenase mechanism, we can see that the cofactors involved in these mechanisms are the same. The movement of the electrons with this mechanism, the movement of electrons within these mechanisms are also the same. Therefore, I suggest you to visit the link provided in the description below to watch the full video on pyruvate dehydrogenase complex mechanism. This will really help to clearly understand both of these mechanisms. If you have any questions, then you can write it in the comments section. Thank you so much for watching, and don't forget to like, share and subscribe to this channel for more videos like this. Thank you so much.